Crash helmet design, prototyping, and testing. The define phase. Kinematic and impulse computations. Hi everyone, I'm Camille McHugh. In this section, you're going to be making some calculations. So make sure you have a calculator. It can be an online calculator. Make sure you have some paper and some pencils. Work through the problems that you see along with me. And then when you get to the end of this section, work through the companion worksheet problems that I provided you on the website. It will all make sense. Don't panic. If you have any problems, please feel free to message me and I'll be happy to help. But also be sure to work with each other and help your fellow peers. One thing that may help you a little bit is that if you look at the units have to work out and make sense. So if your units don't work out, probably the numbers are not working out either. Also be cautious about things like grams versus kilograms, millimeters versus meters. You need to make certain that those quantities make sense and that you're using the proper units, especially if you measured in different units. To a great degree, we measured in grams and millimeters, but you're going to need to be working in kilograms and meters. Now, another thing you need to know is this. Most of these quantities that you're going to be working with in the calculations are actually vector quantities, things like force and velocity. But all of the motion in our egg crash project is taking place in the y direction. Things headed down are negative y, things headed up are positive y. So we've really simplified the process for you by just showing you the equations and working through those steps using the magnitudes of the vector quantities. I don't want you to think that they're scalars. They're not, but it's just easier to work through the problems these first few times if we're just looking at the magnitudes of the vectors. So grab your calculator and your pencils and your paper, and let's get started. So you'll need a little additional background on impulse, drag, and the biomechanics of crashing to finish out the define phase. You'll need to watch a few videos. The links are on the website. Two of them are from Professor Dave on impulse and momentum and on elastic and inelastic collisions. One is on car drag. Remember, with cars, you want to minimize drag, but for the crash device, we really want to maximize drag so that we can create a velocity at the end of the fall and as we enter the crash phase as possible. And then lastly, the Understanding Car Crashes When Physics Meets Biology video gives you an excellent model of what happens to the brain during a car crash. That happens at about 11 and a half, 12 minutes. So be sure to take a look at those. And ultimately, we need to finish out this phase by writing a good problem statement. It must address our client, which is an egg, so the problem must be egg-centered. And a statement along these lines could be something like, protect a head from impact injury. We must also remember that the statement must be both broad and narrow. So broad enough to be creative, something like employ a user-centric device, and narrow enough to say something about really what we want to drill down to. The device must be portable, lightweight with a slim profile, easy to put on and take off, and it will protect the head from a fall from a stated minimum altitude. And we'll put all these three together to make our final problem statement in just a few minutes, but we'll need to add a little bit more specificity to it. So remember, as we define the problem, we need to think about what's happening to the egg. There's two phases to this project. There's the falling phase and there's the crashing phase. The equations we need for each phase are somewhat different. To design a protected device for the egg, you must quantify the motion of and the forces on the egg as it falls and crashes. During the falling phase, we're concerned with kinematic equations to describe motion, and then during the crashing phase, we're concerned with an equation that can describe the forces on the egg, specifically the impulse equation. So we're going to be using two different types of equations for this process. First, we'll begin with the kinematic equations so that we can compute velocity and acceleration during the falling phase. So let's take a few example problems. First, let's look at the equation of motion and try to compute a final velocity for a falling egg when it's just the egg being dropped. No type of protected device. so that for the most part the acceleration that it experiences is that of just gravitational acceleration. So A equals g. What do we know? We know the initial velocity of the egg. If we're dropping it from a ladder, it's starting out with a 0 velocity. We know the acceleration. It's equal to g, 9.8 meters per second squared. We'll know the distance that we're dropping it. We can measure that in meters. What do we want to compute? Well, as it finishes the fall, I want to know the final velocity of the egg. So we can use this equation. Final velocity squared equals initial velocity squared plus 2 times the acceleration times the distance. What I'll do here is I will substitute each of my known values. The final velocity is what I'm seeking, so it is my variable. The initial velocity is 0 meters per second. The 2AD will be 2 times 9.8 meters per second squared times the distance of the drop. Well, I'm going to need to take an example number here, so let's pretend for a moment that I've dropped the egg from something like 2 meters. So, when I plug in each of those values, final velocity squared equals 0 meters per second quantity squared plus 2 times 9.8 meters per second squared times 2 meters. This ends up being 0. When I multiply this out, I have 39.2, and notice the units, meters, that gives me meters squared per second squared. What do I do to each side in order to isolate the variable of final velocity? I need to take the square root. And that also, as you can see, makes the units work. So final velocity is equal to 6.3 meters per second. Now for comparison, let's take a look at what meters per second looks like in terms of miles per hour. If 1 meter per second is 2.2 miles per hour, then 6.3 meters per second would be about 14 miles per hour. Let's solve now a different problem regarding the egg, and let's look at this from a slightly different perspective. What if I have different knowns and unknowns? Why would that happen? Well, let's say that once I put the protected device on the egg and it starts falling, then part of the goal of the protected device, in addition to protecting it during the crash, is to slow it down during the fall. I want to introduce some drag. Well, if I do that, then I have a non-g acceleration. So that means I don't just know what a is. A is no longer g. So I'm going to want to compute a. That's now my unknown. What do I know? Well, I still know the initial velocity, v0 is 0. I would know the time if I use a stopwatch and I measure the duration of the fall. I'm not going to be super accurate, but let's try that. And I know the distance of the fall because I'll know the altitude from which I drop the egg. So I have 3 knowns. I have an unknown. What I want is my new acceleration. And therefore, if I use this equation, d is equal to v0t plus 1/2 at squared, I know everything except for a, and I'll be able to solve for a. So let's plug in the information I know. On the left, the distance is 2 meters. Why? Because let's say that that's just simply the drop that I'm performing at this particular moment. Okay? v0 is 0 meters per second. The time would have been the drop that I measured, so I would need to actually take this measurement, and let's say it turns out to be 0.75 seconds, plus 1/2, a is my unknown, t squared. Again, there's t, 0.75 seconds, and I'll need to square that. So let's move through solving this equation. On the left, I still have 2 meters. Here, the product of these two numbers is simply 0, plus 1/2 a this squared. So I'm going to convert the 1/2 to a 0.5. There's my a, and then 0.75 seconds quantity squared gives me 0.5625 seconds squared. Move down to the next step. What do I need to do? Still 2 meters on the left. The 0 just goes away. Let's go ahead and multiply out these two coefficients, 0.5 and 0.5625. Combining those, I still have A sitting here, but then now I have 0.2812 seconds squared. Please be aware we realistically could not use that many decimal places, but for now let's just do so that we can get as precise an answer as possible. All right, so now what happens? I've got A on the right being multiplied by something, so I need to isolate A, and the way to do that is to divide both sides by this number. Now, once I do that, you should also notice that your measurements, your units work out correctly. So meters on the left, and then when the second squares goes to the denominator on the left, I'll have meters per second squared. That will work. That is a unit for acceleration. And computationally, then when I divide both sides by 0.28125, I get the acceleration is equal to 7.1 meters per second squared. Now let's think about that value. For comparison, the regular gravitational acceleration is 9.8 meters per second squared. So the new acceleration, which must be less than just g, because I've introduced all this drag, is now 7.1 meters per second squared. Okay? Therefore, adding drag features to the helmet reduces its acceleration when it falls. That's good to know. We want to reduce that acceleration during the fall. Now, what can I do with that non-g acceleration? Why do I care about it, and why did I need to compute it? Well, here's what it can tell us. Now that I know what the acceleration of the egg is when it's in a protective device, I can go back to my first kinematic equation I used in problem 1, v final squared equals v0 squared plus 2ad. And I can plug in my newly known value for A, and I can ultimately compute a final velocity when the egg is in a protected device that also cultivates drag. So that's a really powerful quantity to be able to compute, because that means I'll know the new velocity at which the egg in its crash device is finishing its fall and initiating the crash. Let's take a look at what this would compute out to be. So my new known values are still v0, that's 0. My acceleration, which is not g, and remember from the last problem I computed that to be 7.1 meters per second squared, somewhat less than the standard value of g, which is 9.8 meters per second squared. I still know d, because that's whatever drop altitude I employed, 2 meters, and I want to find the final velocity. So go back to v final squared is equal to v initial squared plus 2ad. We're looking to solve for v final. v0 is 0 meters per second, square that, plus 2 times a, 7.1 meters per second squared, times d, 2 meters. Multiply out the right side, this is 0. This part comes out to be 28.4 meters squared per second squared. Always check your units. So when I take the square root of each side, v final will equal to 5.3 meters per second. And again, for comparison, if 1 meter per second is 2.2 miles per hour, then 5.3 meters per second is 11.8 miles per hour. So remember before, when the egg was hitting the ground and starting the crash phase, it was somewhere around 14 miles per hour. But now it's down to 11.8 because I've introduced drag into its protective device. So clearly, drag reduces acceleration, which reduces the crash velocity on impact. That's good news for us. So we've taken a look at the equations for the falling phase. Now let's turn our attention to the impulse equation, which we'll need for the crashing phase. Let's think about this impulse equation. From Professor Day's video, we know that if someone falls off of a roof, then they've got some momentum. What's momentum? It's their mass times their velocity. So this person has a mass, they have a velocity during the fall, and then at the moment that they hit the ground, that velocity has to go from some value to 0. Ultimately, they have to end up with 0 velocity, 0 momentum. So if the person just hits the ground, then their change in velocity is some number,
And if the person has some sort of a slow hitting of the ground due to something like a trampoline, then they still have that same change in velocity. One way or the other, they're going from some velocity due to their fall to 0. So this side of the equation is always the same. The person still has the same mass, and the person has some sort of change in velocity. So m delta v, regardless, is the same. So what's different? Well, it's the left side of the equation. So this is what we term impulse, and it's their force that they're experiencing times the time frame over which they're experiencing the force. So just think about this from common everyday experience. If you're in a car crash and the time in which you go from moving along in your car really fast to being completely stopped, if that time is very, very fast, then you are experiencing a lot of force of impact. Okay? So if delta t is very small, then that forces the force to be very large. But if through a trampoline or an airbag or some sort of cushion, you can spread out the time of the crash, make delta t large, then that means that when I multiply the delta t times the force can be smaller because this product has to be the same as this product. Either way, F delta t is the same as F delta t. So if t is small, that makes F big. If t is large, that makes F smaller. And isn't that what we want? Don't we want the time to be larger so that the force with which that egg is crashing is a little smaller, giving it a greater likelihood that it sustains the crash without damage, without cracking? Okay, we're wrapping up these computations. Let's now use that impulse equation, force times the change in time is equal to mass times the change in velocity, to revisit problem 2b. Remember, problem 2b was when we computed the final velocity of the egg as it finished its fall, and the egg was wearing its nice protective device. So let's think about the two scenarios. We have the egg falling in its protective device. Acceleration is less than gravity because drag is helping slow it down. We have a final velocity right as it starts the crash that's less than it would have been if I didn't have a protective device. But now let's think about this crash phase. What happens during the crash? Well, the egg experiences impulse. And remember, impulse is force times delta t, force times the change in time. If the change in time is really small, the crash just happens lightning fast, bam, and that egg experiences all of its force in this tiny, tiny time frame, then it's really likely to crack. But if I can spread out the time of the crash, make delta t large, then it will cause the force to be less and probably, hopefully, cause the egg to stay intact and not crack. Either way, F delta t equals F delta t. So if these two things are equal, then that means that if delta t is small, then F is large. If delta t is large, then F is small. We want F to be small. But let's take a look at these two scenarios computationally. For each of these problems, the final velocity at which the egg will finish the fall and start the crash is 5.3 meters per second. And now I will need the mass of the egg. For my computations, I found that the median mass was 55 grams. Yours may be different. But for this problem, for this example, we'll use 55 grams. And what do I want to compute? I want to compute the force with which that egg is experiencing the crash, and I want to do that for various values of delta t. So let's look at this first scenario. If delta t is small, wham, the crash is happening super fast. Okay? No cushioning. It just goes from moving to not moving. Then F delta t is equal to m delta v. Remember, this is the change in momentum. And I'm going to plug and chug. What's the mass of the egg? I need to convert from grams to kilograms. Remember, this equation is predicated on using kilograms as my measure of mass. So convert 55 grams to kilograms, that is 0.55 kilograms, times the change in velocity, Remember, the egg starts at 5.3 meters per second and then ends at 0 because it's no longer moving once it's on the ground. So multiply those two together, I get 0.29 kilogram meters per second. Let's say that I make the time that crash occurs, the delta t, 100th of a second, 0.01 seconds. Then when I plug that in for delta t and solve for F, then I will find that the force is equal to 29 kilogram meters per second squared, and that unit is a Newton, of course. So the force is 29 newtons. Essentially, an apple is a Newton in terms of force. So that's like 29 apples all sitting on top of my egg. That's a lot of force, right? I would suspect that the egg would crack. But let's take a different scenario. Let's solve the exact same problem, but let's make delta t large. Let's spread out that time. Give it some cushioning. Let's let that egg have a little time to come to rest, to go from moving at 5.3 meters per second to 0. So, solve the same problem. F delta t is equal to m delta v. The mass is still 0.055 kilograms. Change in velocity, 5.3 meters per second. And let's adjust and change delta t now to 1/10 of a second. Here it was 100th of a second. Here it's 1/10 of a second. So 10 times more time to come to a stop. What does that mean? Well, then force ends up being 2.9 newtons. That's almost 3 newtons. So almost the force of 3 apples. Which would you rather be squished by, 29 apples or 3? You can see that it's very likely then in this case, by giving it that little extra cushion, that little extra time, it greatly reduces the force, and therefore the egg might very well be able to survive and experience an impulse that creates a force that is endurable. So we've looked at 2 different equations. The kinematic equations, these 2 together, and the impulse equation. And each of these has informed what we need to know and understand about the mathematical side of the egg falling and the egg crashing. How? Well, during the falling phase, if I maximize helmet drag, then that minimizes the final velocity, Vf. During the crashing phase, using the impulse equation, if I add lots of cushioning, that maximizes delta t and minimizes the force of the crash. A couple of final thoughts. You saw Professor Dave's video on elastic and inelastic collisions. Elastic means that we have something like padding that will bounce back. That padding allows us to increase delta t and therefore reduce F during the crash. However, we can also have an inelastic collision, and the helmet itself can play a role in protecting the egg. So, although if the helmet cracks and breaks, we can't recover the helmet, and this is clearly inelastic, it's not just simply bouncing back, it will still protect the egg. The helmet may not survive, but the egg does. So you need to think about the role of both the padding and the helmet itself in terms of protecting the egg, elastic versus inelastic. Additionally, with regard to designing for user safety, you want to think about the protective device that you create in some additional terms. You want it to be easy to put on the protective device. It takes you forever to put it on. You're very likely never to wear it. You want it to be easy to remove the protective device. Same thing. You want to be able to get out of it when you reach your destination. You don't want it to be too bulky in size or too heavy, too massive. You want it to be reasonably comfortable. And you really don't want it to be interfering with the mobility and vision of the client or the customer who's using it. Otherwise, that's going to create a whole different set of safety issues. We've done a lot of work up to this point throughout the define phase to come up with a substantive, solid problem statement to guide our design team. Here's mine. Yours will be somewhat similar, but will change based on the measurements that you took as well as the computations you perform, especially based upon the altitude that you want your egg to survive. Design a personal protective device which will safeguard a boiled egg head of median mass 55 grams from impact injury. when falling onto a hard surface from altitudes up to 2 meters. The device must be reusable, sized to fit a median egg of 55 by 44 millimeters, compact with regard to its dimensions and mass, provide easy ingress and egress, that means getting into it and getting out of it, and must not interfere with user mobility and sensory functions. That's my problem statement.
You did it. That was an awful lot of challenging work that you have engaged in during the define phase. It's actually 3 different sections to get to this point. But now you have a well-articulated problem statement, one that you and your team can use as you enter the next phase, ideate. And during ideation, you're going to be creating all sorts of exciting ideas, wildly brainstorming to think of all the possibilities for designing your egg crash protection device. Let's get going.